We have spotlight presentation again. We have 3 speakers, and the first speaker is Maxime Bernard. Okay. So please keep 3 minutes. Okay. So if you are
Thank you.
Can we start? If you're ready, please start.
Okay. Hi, everyone. I'm Maxime Bernard from IROS in France. And so I'm a PhD student supervised by Claudio Pacchierotti and Paolo Robuffo Giordano. Sorry. Okay. So I'm going to present the work we did recently, which is based on this paper by Paolo Robuffo Giordano. It presents a way to maintain connectivity in a group of multiple robots. So let me present it quickly. Connected robots, or globally connected, means that we have a path between every 2 robots. It's graph theory. And we apply on each link a weight that is a multiple of subweights. And each subweight enforces a constraint that we want to apply to the group. And what's good with this design is that we can break and create new links as long as the global connectivity is maintained. So there are no drones or no subgroups that are separated from the rest. So in the recent work, we moved to limited field of view camera so we don't have omni-directional sensing of the drones. We also moved to a global frame, from a global frame to a local frame for each drone, and also modified the model, the robot model, to also control the view of the drone, because now we have directional sensing, as I said. What this allows us to do is to have a new weight, a new subweight that controls the fact that one drone will try to maintain his neighbor, his camera's field of view, and also to stay in his neighbor's camera's field of view. So basically, he wants to see as many neighbors as possible and be seen by as many neighbors as possible. And we also present a new way to estimate the relative yaw between 2 drones using the data we know, because we need this to compute the weight and the gradients for the control scheme. And finally, we did simulation experiments using ROS2 implementation, Unity visualization, and this will help us, because our goal in the end is to use virtual reality as an interface with the human user, and also haptic feedback on the joystick to feedback like some information. So in this experiment, the user had to move a team towards an objective point, and the robots themselves maintain the global connectivity of the group. And yeah, that's it. I'm happy to discuss this with you during the poster session. And I also have a video if you want to see it during the poster session.
Yeah, thanks so much. Next speaker is Julien Martat. Can you share your slide?
Yes, can you hear me?
Yes. So if you are ready, please start.
Can you see my slides?
Yes, I can see you. The slide.
Okay. Thank you, everybody. So I'm Julien Martat from Onera. I'm going to talk about distributed control for human multi-robot swarming. So this is part of a project called IROS, which has been funded by the European Defence Agency. So the main objective is to control a swarm of autonomous UGVs, which interact with a localized operator in the wild, so in uncharted, cluttered environments. So typical use cases can be transportation, like a mule capability, observation, or maintenance of communication links. So far, we are focused on 2 main user-oriented swarm modes. One is to make the swarm follow a predefined path of successive waypoints at a given reference speed. And another one is for the swarm to follow such a path, but by copying the speed of the operator. So when the operator moves, the swarm moves along with him. or her. And whatever the mode, we always enforce safety constraints like distances from the operator with multiple obstacles and also between the other robots. So for this purpose, we have developed a Voronoi-based swarm navigation algorithm. So the idea is that on each embedded computer, the vehicles can compute a Voronoi partition where each vehicle is assigned a given cell with some mirror agents to bound the cells. And in our framework, actually, the human operators are considered as additional agents in the swarm. So they also have their own safety cell. And in these cells, each vehicle is able to compute its next target point as a geometric combination of an attraction towards the current waypoint and a repulsion from the other agents, be it robots or human operator, which are also localized in the same frame. To handle obstacle avoidance, we rely on collision cones. So given the obstacle localization from the embedded sensor, we check that we have a line of sight between the current robot and its assigned waypoint. So if there is a direct line of sight, we don't modify the waypoint. Otherwise, we use the aggregated collision cone to find a new target waypoint, which is used in the previous procedure to make the robot navigate. So this has been tested quite extensively in field experiments with 2 robots so far and a human operator, with everybody localized using stereo vision and onboard processing. And so we've tested the 2 autonomous and velocity guided modes. So for example, here you have a trajectory with successive waypoints which are followed by the 2 robots. And they were doing so by copying the velocity of the motion of the human operator. And we also checked that the robots did copy well what the operator was doing. And in all these tests, we successfully avoided obstacles and collisions. So the system is ready to handle more UGVs, more operators, since it's scalable by design. And we can also include other types of behaviors, such as follow the operators or more elaborate formation modes. And you've got a link for the video of the experiment, so you can also come and see me during the poster session. Thank you.
Thank you so much. Next speaker is Yuron Lee. Yeah,
Right.
Can you share your
Can
slide?
you guys
Yes.
hear me?
Yeah, I can hear you.
Let me share my screen. Great.
Okay, please start.
Okay. Hello, everyone. My name is Yulong from Columbia's AI and Robotics Lab. And today I'm going to introduce our work scene editing as teleoperation. So when we think about teleoperation systems, we mostly think about robot-centric teleoperation systems. For example, like the one in the left figure, where the robot mirrors the actions of the teleoperator to carry out continuous motions. But those kind of systems often require low latency connections and complex input devices. Some prior works try to alleviate such problem by allowing the users to control the end effectors of the robot on a virtual user interface, like the one on the right figure, but it still demands some user knowledge of the robot and is less intuitive. Moreover, for all those robot-centric teleoperation systems, an operator can only control one robot at a time, which is specific to the robot hardware and configuration, and it's very hard to control multiple robots using teleoperation. So in light of these problems, we propose to scene editing as teleoperation. And the key idea is to transform the robot-centric teleoperation interface into a scene-centric interface. So instead of controlling robot to specifying actions, we allow users to control objects to directly specify the task goals. So first, we study the system on 6 degrees of freedom kitting tasks, which is quite ubiquitous, but still mostly done manually. It is also quite challenging because it requires high precision actions. I'd like to first show our system in action. So on the left is the robot workspace, and on the right is our transformed editable virtual scene. So first, the user will edit the virtual scene to specify the goals, and then the robot will plan and carry out the corresponding actions. In building the system, we solve 2 main challenges. The first one is translate the real world thing with possibly unknown objects to a virtual editable thing. So we propose a category agnostic thing completion algorithm. Given a single depth image, we first use a segmentation model to predict the object masks, and then with 3D complete the objects to create editable virtual objects. And the second challenge specific to the task is to tolerate imprecise user input and predict accurate 6 degrees of freedom poses so that the kitting will be successful. We propose a shape-informed action snapping algorithm, and the intuition behind it is that the shape boundary of the kit should inform the pose of the object. Here are some qualitative results. So on the left, given a single depth image, we create a virtual editable thing. And then with some simulated imprecise user input, our algorithm is able to predict accurate poses close to ground truth. Here's another experiment. And I want to know that even though we only experiment with a single robot, it's easily extendable to multiple robots because the robot hardware and configuration is abstracted away from the system. Thank you very much.
Thanks so much. Okay, then we have lunch break from now, and we will start next session from 1:10. We will shift 10 minutes. So please come back here until 1:10. Okay. And we have two announcements. We have, thanks to IROS Technical Committee of Multi-Robot Systems, we have free lunch boxes over there. So we have Japanese food, vegetarian, gluten-free lunch boxes. So feel free to take your lunch boxes. And we have poster session during lunch break. So please visit posters over there. And also we have online presentation. So please visit Zoom, Zoom breakout room, please. Thank you. Thanks so much.